I'm Stephen Foskett, the organizer of the Tech Field Day event series. The video you're about to watch is part of the Storage Field Day presentations held in San Jose, California in October of 2016. We welcome Primary Data here. They've presented many times, and if you'd like to see more videos like this from Primary and other companies, you can go to our YouTube channel, youtube.com/techfieldday. If you'd like to learn more about the Tech Field Day event, just go to techfieldday.com.
Good morning, everyone. Again, my name is Lance Smith. I'm the CEO for Primary Data. It's a real pleasure to be here today. You know, as Stephen said in our introductions, we've done the Storage Field Day several times. In this particular installment, we decided to change it up a little bit. We presented not too long ago at VMworld, and at that time we announced that we had GA'd our product, and we were open for business. Now, at that time, we also announced that not only was the product done, but it was also being certified under a number of different platforms and available to our customer base. Now, what we have learned in the past 6 months, we've gone to a number of verticals, whether it be media and entertainment, oil and gas, finance, health services, life sciences. Our customers have come back and explained to us the kinds of challenges they've had with storage, whether it's different storage types. We've been here and talked about surveys that we've done, where our customers themselves, are managing, as many as 10 or 20 different types of storage in their environment, whether it be flash in a server, all flash arrays that they want to try and bring into their infrastructure, and even bring it into the cloud and the benefits of the cloud. What we want to do for you here today is literally give you some of that feedback from those customers, actual customer examples, and even do a demo today. We'll have David Flynn, our CTO, come up after me, and he'll start showing you really the technical challenges that our customers have actually faced. One of the areas that we want to focus in is scale out. There are 3 areas for which our customer base really has been looking towards us to help solve, whether it be data migration, data lifecycle management, in this case, scale out for the needs of performance or increasing the capacity in a nice scalable manner. The one market that we're going to focus on today is going to be media and entertainment. This seems to be a really hot spot for us and our technology. We have several customers that we've been engaged with. We completed our POCs in the first half of this year, and now our customers are turning towards their production environments. Some of the challenges they run into. Look, if it's the studios, it's a massive amounts of data they're collecting as they're shooting these movies in the digital format. Most of the cameras that they're shooting now, it's not the film base. It's based on flash, capturing that information at 4K and 8K resolutions. Then we start talking about post-production, distribution, making these content available. And even when they actually have to do a follow-on sequel to a movie, getting access to that data in real time and not just archiving it and forgetting about it, trying to find that data once more. And we'll also start talking about what the customers are doing today, how they've been locked in with vendors, how they have to be forced to add more storage silos to try and solve their problems. Now, what I'd like to do is I'd like to turn it over to David Flynn. He is our co-founder, our Chief Technology Officer. He's going to spend some time whiteboarding for you what those environments look like, what those challenges that those customers in the media and entertainment are facing. Then later we'll go through and we'll actually show you real-world examples of total cost of ownership, what the return on those investments are for our customers in the media and entertainment space, and then we'll also show you a live demo of the actual product itself. What I'd like to do is turn it over to David Flynn.
Thanks, Lance. I'm David Flynn, the CTO of Primary Data, and grateful to be here once again. Thanks, Stephen, and Storage Field Day for the opportunity to be here. We've done this several times, so I've been thinking about what to do to make it interesting because, my God, this is the last day you've been here. You have to have seen a lot of stuff, and you've seen us before. So I figured maybe, since it's what I like, is get down in some nuance and detail. So that's what I'm going to do, is talk very specifically about the media and entertainment space and the problems that they face in architecting and running their storage infrastructure. And of course, along the way, I welcome any interruption and questions, as that helps to guide the discussion. So please put on your critical thinking hat and don't hesitate to interrupt as I try to go through sort of an assimilation of what what I've learned, not just at Primary Data, but formerly at Fusion.io in working with this class of customer. And let me state that while I'm going to be talking specifically about media and entertainment, this applies more generally to the technical computing market, the folks who use Linux clusters to do things in mass. So here we're talking about guys that might be oil and gas, doing seismic type stuff. We're talking about the life sciences or bioinformatics. We're talking about the industrial design, simulating car crashes or simulating mechanical mechanisms like building airplanes or jet engines, that sort of thing. Generally, and even the scientific world of scientific computing and HPC. But our focus here is more specifically on media and entertainment. But again, most of these customers have similar problems, and they are all generally those who've been classic consumers of scale-out NAS in the past. So with that, let me jump into specifics here about how most of them are architecting their infrastructure. Let's start from the top down, where we have the cluster of Linux nodes, the clients. Generally, what they do is Isilon has typically dominated this market. It's rather ironic that NetApp, even though the inventor of NAS, kind of missed out on the scale-out NAS market. Isilon came in and did a much better job there. Cluster mode NetApp took a long time to come out, and really isn't a complete product, if you ask me, because it doesn't do dynamic capacity balancing across the back end. So it's not truly a scale-out NAS even. But so I'm going to use Isilon because that does seem to have the largest footprint in this space. And the Isilon system is architected as a two-tier architecture. It has front-end nodes that provide the routing service, and then back end you have the storage nodes, which actually have the capacity on them, and you can get those in different flavors with different levels of performance. And this is necessary because you have to route where the data goes so that you can distribute it. So these gateway nodes are there to scatter and gather the data across the back end so that you can scale it. And to make up for the fact that they're having to bounce the data through an intermediary node, what they've done is they've built this with an InfiniBand, very high performance backplane in between here. So most organizations are using this kind of an architecture. And typically, one isn't enough. While I can scale out capacity here, it's still one single silo and has issues if you need to take it off, turn it off, or whatever. Most folks end up deploying several separate scale-out NAS systems of different flavors and different generations. And they often end up augmenting their scale-out NAS systems because this architecture inherently introduces inefficiencies in performance. They augment it by putting, the odd scaled-up NAS system, like a big NetApp, in there as well. And these are often used for the temp and scratch space, where it's a little bit more confined, and it's easy to graft it into the namespace to be used just in certain areas, and you get higher performance. Any questions so far about this? Okay. Now, this stuff was all architected way pre-Flash, okay? Isilon is, 15 plus, going on 20 years ago. What most folks have ended up doing to try to get higher performance out of this is they put a layer of caches out front. And these cache caching systems, NAS caches, can augment the performance of the data that gets held in their cache. This, of course, has some challenges to it. While it moves some of your data closer, it ends up making the bulk of your data further away. So while it can augment performance, it makes the performance of the back end have an additional tax on it. Okay. Notably, you don't see server local NVMs getting used hardly at all because they would be very difficult to manage in that scenario. And notably, rarely do you see cloud and object storage incorporated because it doesn't talk the same NAS interface, and it's a manual process to move things in and out of it. So it's a fairly new thing there. Okay. So this is what the architecture typically looks like today, and it has challenges on a number of dimensions. And I'm going to lay these out here as I fill in some of the details on them. One is, of course, from a performance perspective. The other one from a manageability perspective. And lastly, from a cost perspective. If we look at this architecture, when you track the access to a bit of data, you're going through several different layers. This means that you have an impact to performance in that it's really a 1, 2, 3-tier architecture. So you're having to go through 3 tiers of data to get down here. Now, I forgot one very important piece. Let me back up a bit. The story's not done. Not only do you have multiple scale-out NAS systems and scale-up NAS systems and caching in front of them, but every single one of the movie studios we talk to has proprietary, specialized scripting auto-mounter symlink foo that they use to stitch together a namespace and try to provide a view of the world that can stay consistent even in the face of commissioning and decommissioning new storage and so forth. So I would talk about this as the poor man's namespace virtualization layer, and it presents issues from manageability. For example, this technique, often the applications bind to the symlinks, don't correctly bind to the symlinks, they bind to the actual underlying thing. And when you actually go to try to shift where something lives in the namespace to change it, they say you don't really know what apps are going to blow up because you don't know what apps have not been correctly protected from the abstraction, through the abstraction and mess up. So this, I don't count this as one of the tiers because this is just software sleight of hand. So from a performance perspective, it doesn't really matter. But from a manageability perspective, I now have several layers with different vendors on each one, including my own in-house stuff that has to be done here. I have manual processes of copying and moving the data around. Now, let me go back for a second and try to, well, maybe what I should do is draw the contrast to start with, okay? And try to explain where primary data comes into play here. When we introduce primary data, because it works very well with existing storage, it allows for one to have an architecture that's much simpler. As a matter of fact, I'll draw it over here in the corner. If I have my application servers I can have the storage be directly underneath it. Because we've moved the routing function into the client as a look-aside to the control plane where the metadata is, data sphere, the routing doesn't have to go through an intermediate layer, which also means that if I incorporate flash high performance here, I'm not handicapping it by putting it behind many layers of cruft. As a matter of fact, I can even put server-side flash and have primary data route the access to the server local flash. And if you have cloud, the data can be routed directly there. Because we're doing the virtualization with this separate control plane, you don't have to have this. It can all exist in one single mount point, one single namespace, and add and remove different storage assets. As a matter of fact, you can keep the Isilon systems with their two-tier architecture. Think of that as just one system underneath. So your several different Isilon pools or your existing NetApps, those are still able to be used, but if you want higher performance, you can collapse out all of these extra layers and even fold in your server-attached media and cloud. Let me stop there as I make sure this follows. Yes?
In the model you showed down there on the left-hand side, you very much talked about the application servers and then another middle layer of caching or whatever you want to call it. Those devices are actually built to do that, whereas on your right-hand side, in the model that you described of your technology, what is the customer having to do to the application server to provide that equivalent caching? Are they adding extra memory? Are they adding extra faster storage in there to cache the data that would be coming off the disk?
Well, indeed, one, the metadata is, of course, served by something that's highly specialized for it, very high performance.
Which is fine.
So let's take it off the table.
Yep.
The data path, being very direct, allows us to take servers with flash in them or flash in the application server itself and incorporate that as part of the data space.
But that's only the case if the storage is reasonably close in terms of low latency to the application.
Here, from a network perspective.
Yes.
Right. The same as would have been required here.
Possibly, depending on what type of caching technology you were using over there.
Right. So the specific answer is a customer could incorporate a server, a flash-heavy server, with the primary data DSX software stack. That's the data path piece that sources raw media into the global data space. And that would substitute for this cache function.
So what happens if the data is in the cloud and you've got an application server and the latency isn't very good?
Well, then you would want to architect your objectives to make sure that the data is warmed up on premise. Which actually goes to another interesting problem that they have from a manageability perspective. Identifying what is cold. Estimates are, well, let me open this to you guys. What do you, in your expert opinion, believe the percentage of dark data is in most customer sites?
90%?
What's that?
78%.
70 to 80%.
90%.
80 to 90%. Yep. I think
98. I'm throwing that number out.
98.
Say it.
Yeah, very possibly. Now, most of these guys, because they're working with such huge data sets, they are always hitting their capacity limits and spending a lot of time trying to refine their filtering of what is relevant and what isn't relevant. We've talked to one customer in one of the movie studios. He says he'll go through maybe 15 to 20 iterations building the filter that determines which files need to be retained when they go to take a movie offline versus the files that can be fully discarded versus files that they want to keep warm.
But while they're in production, though, they don't have a lot of cold old data.
No.
I mean, it's building
That's
up there,
right.
but they really know what's interesting and what's relevant. So to answer your case, Chris, there's almost no chance that in production work they would have to be fetching data from the cloud unless
Correct.
they had a disaster and needed to move the production site to another center.
That's right. Right. But there's still benefit even during production in identifying the files that are scratch stuff that aren't needed. They're not the original input. You definitely want to preserve that. That's got all the art in it. The rendered output, you generally want to cache that. Intermediate stuff that was just used in the derivation of the final, not necessarily. And once that stage is done, you might delete that because it's not final product or the inputs to it. So there's still lots of reasons. So identifying the cold data for them is very tricky. In contrast here, because this has got programmable and intelligent metadata, those types of filters can be built in the control plane and identify those files and set objectives on them very directly. So this is replaced by the ability to do intelligence in the metadata, where you program that discrimination logic. Sorry, I don't want to use that term because discrimination is such a bad thing. But we got to discriminate against certain kinds of data that shouldn't be there. Questions on this so far?
I'm not sure how important it is, but you made the comment that you thought it was difficult. You're still talking about the M&E space, right?
Yes.
Okay, because I don't know why you would think that it would be difficult for them to identify cold data, because cold data is the movie we're no longer working on and everything else.
No, actually, it gets very difficult even once the movie's done, because they don't want to archive and have to retain all of the bits. So especially at the end of the movie production, when they're taking and storing the movie,
okay, so
because there's stuff that they want to discard entirely, which they'll never get back. So they have to be very careful. So when they archive it, it's what do they even bother to archive?
So we agree it's easy to identify what's cold. The question is it cold and valuable?
Correct.
Cold and crap. Okay.
Right.
Gotcha.
And it's stuff like what user it was, what the file's function is, and it ends up being this Mondo predicate from hell with lots of different clauses that take these guys many iterations and lots of worry to do, because if they screw it up, now they're missing pieces of the asset that may be needed.
They're doing an analysis of what's the cost to recreate this from the primary inputs versus the probability of needing it.
And making sure they've identified the primary inputs as well on it, yeah. So I'm going to use my cheats here for a little bit just to make sure I'm covering it all. So from a performance perspective, this three-tier architecture has a very real impact. The absence of a server local means the difference of a zero tier. If you can incorporate this, you never have to go over the network, which means having extreme bandwidth for the types of things that don't need reliability. And indeed, during the production of the movie, everything except for the inputs are reproducible, especially if you're in the process of getting the production of them right. So much of that, the temp and scratch and swap, is the bulk of what the cluster is doing, and that stuff can actually be held server local with no network access versus 1 to 3. If it's in the cache, it's 1. If it's in the back, it's 3, which also has the negative impact that it's unpredictable, because it's the cache replacement algorithm that may or may not get it right based on what's been done. So from a performance perspective, there's another huge issue that they face, and that is the hotspots. I'm using the wrong marker here. I want to use this one. So I've had them tell me that the bulk, 70% of the load often ends up going through one cache and through one gateway node, which kind of defeats the purpose of being able to scale out the cache and scale out the gateways. Any guesses as to why it's so difficult to get a good load balance across the caches and the back end? It's because generally it's done on a per client basis, and once you've made that decision, it's rather difficult to rebalance it. In Isilon, this is a very well-known problem, the fact that clients connect to an IP address, and while I can move those IP addresses around, that only gives me a certain level of granularity when it comes to directing the load. So you end up with hotspots where you're only getting, or you're pushing 70% of the load through one gateway, which the converse of that is that your cluster is sitting there starving because that one is overtaxed. In contrast, with primary data, we route the data on a per file basis, which also means we can affinitize the file to a specific gateway and make sure that there's not contention and that there is good caching of it. Let me restate this to try to make sure it's clear. With typical NFS v3, the best you can do is decide which server a client connects to, and every single object that that client accesses is going to go through that server over that connection, which means you have the issue of load balancing because you have very coarse granularity. With primary data and the ability to route individual data objects, we are able to distribute the load at a much finer granularity. Based on the object being accessed, we can put certain objects accessed through different nodes. And not only can you do it per file, but you can do it dynamically, load balanced. In other words, we can decide at any point in time that this object is, or this gateway is servicing objects that are consuming too much performance, and move one or more of those objects to be accessed through somewhere else. We use the exact same technique for data mobility in that the control plane can recall the routing and change the route live. Questions on this?
So basically, if you lose one of the gateways too, this is like to make it easier to reestablish connections. So
Yeah. What Isilon does is that, what is it? Their Smart Connect, I guess it's called. Smart Connect distributes virtual IP addresses across the physical nodes. And if one of the physical nodes goes down, it'll simply hand that virtual IP address to another node so that it doesn't get stuck. So they use the coarse granular IP, client-server connection-based thing to reroute it. And they typically hand out the IP addresses in a round robin or some sort of way to try to distribute the load. But again, that's at the granularity of a client and rather static. Other questions on this?
I guess I missed a piece. So in your drawing over there on the right, you talked about dynamically
Rerouting.
Right.
Routing on a per object basis. So it doesn't matter which client is accessing it. If they're accessing a specific object, it's going to go through a specific gateway. That way, that gateway can benefit from caching that object and not having to contend for locks and other things when it comes to getting at that object.
Okay.
Yeah, that's another big problem is if I'm accessing the same object through different gateways, then I'm having to bounce the locking between them, et cetera. And I'm not getting the benefit of having it cached because I'm having to thrash the caching between them. So what is the net of this? And that's what's really cool is even if all we're talking about is your Isilon, with primary data out front doing the routing through to the Isilon, we can improve the overall output of the Isilon significantly. What were our numbers, Doug, what were the numbers that we were showing in the testing on being able to improve the throughput out of the 40%? 2x. 2 to 4x the performance output of that exact same Isilon, just by doing a better job than Smart Connect at distributing the load, by being able to do it dynamically and at the object granularity with affinitization.
So from a protocol perspective, what are you doing between the clients and the storage?
What do you do between the clients and the storage?
In your architecture?
In our architecture, there's an NFS 4.2 connection, a PNFS connection that gets all of the metadata and control plane stuff. And the data access is still over v3. But what ends up happening is that in our world, every single client has a connection to each of the gateways. Not just one of them. And therefore, the control plane can decide which one of those it wants to route the accesses to a specific object through, because routing is done object granular. When the client opens a file and starts to read and write, he goes to the control plane and says, where should I go to get at it? And that's how we can distribute object granulars, because every client connects to each and every one of the gateway nodes, and then it's just a decision of which IOs does it route to which one. As a matter of fact, this is another significant performance improvement, is we had actually Tron, the Linux kernel maintainer of the NFS stack, enhanced the parallel NFS client to be able to make multiple connections, ostensibly to the same server, and spread at the specific I/O, spread the load across multiple connections. So think of it as like Ethernet trunking, but at the NFS layer. And that way, if you have multiple interfaces on the same gateway, the load can get spread across those. Now, this is extremely relevant because, here's the irony, Isilon kind of got made by the media and entertainment space. Because prior to Isilon, there really wasn't a good scale-out NAS solution. And they beat NetApp to the punch, like I was explaining. But today, Isilon has a problem with 4K video because of the network interfaces and the fact that the client is routing that one very, fat pipe access through just one interface. So it's kind of the irony that they're having trouble scaling up to the kinds of video feed speeds today, and it's specifically because there's not better distribution of load across the interface or distribution of load across the multiple network interfaces on their gateway nodes. And this solves both of them, because not only do the clients in our world have connections to each, but also to each one of the interfaces, and can route objects through different ones and spread even the access to one object, spread it across multiple interfaces. You probably don't want to spread access to one object across whole separate gateways, because then they're contending with each other. You're not getting the benefit of the cache, lock thrashing. But spreading it across all of the interfaces to the same gateway makes a whole lot of sense. So we have two levels of spreading. One is spreading at the I/O. Every single access can be diffused across multiples to the same object, and then different objects across interfaces. Questions? Net of it is very significant performance improvement, 2 to 4x from your same piece of hardware. Nothing more than just primary data to give the sophistication at the software and control plane layer. Yes?
What was the client-side requirements? So on these Linux boxes, you're talking about Linux kernel enhancements, but there's
so
an agent
the client
side as well.
The client is upstream, since it's the Linux kernel maintainer who's building this stuff. But and we do have ports of that newest, most enhanced client going back to older versions of the kernel and Red Hat, et cetera. So it'll take a little bit of time for these to be in box in the Red Hats and trickle down to them. But what we found is these customers are eager enough to solve these problems. I mean, to put this in perspective, we've had studios tell us that they have $6 and $7 million budgeted over the next couple of years just to try to step outside of the performance limitations that their Isilon has right now. Or have a $2 to $3 million budget to try to improve the performance of their temp and scratch part of it, where the data is more transient, and they could be using the server local or commodity off-the-shelf servers as that performance tier. So this is big money trying to solve these performance limitations. Other questions?
Sorry, I'm still unclear on the answer to my question of what's the requirement on the client side. So upstreamed, if I've got a
so
Linux
it's a specific kernel module that's the NFS client. So either it's a kernel that has a newer, the newer NFS client, or it's the RPM packages of the newer client that you install in the kernel itself.
Thank you.
So, specific.
Do you need to change any of the configurations on the Isilon node as well?
The Isilon, all of that is unchanged. One thing that you do want to do is turn off their Smart Connect.
Okay.
And have it be a more direct mapping of IP address to specific interface on a specific gateway node.
Okay.
That way our thing isn't fighting having it possibly bounce virtual IPs across different ones.
You could actually save some money on the Smart Connect as well.
That's exactly right.
Yeah.
Exactly right.
Yeah, one could argue that you just do that anyway. The best practice would be to not have Smart Connect working.
Okay. So here, the last one is or not the last one, but the second last one is the fact that you cannot get server local in VM mapped in, which we can. But here's something that's worth taking a little tangent on as we talk about performance. When I originally started primary data with this concept of splitting the control plane from the data access plane, I did it under the assumption, which I've now determined was false, that would inherently make it slower because I have to do a metadata lookup before I do the data access. So I've had people ask me that in the past, and when I first founded the company, I assumed that maybe for small file workloads, it would be inefficient to have to go over to the control plane before going and accessing the data, to the control plane before accessing the data. What I didn't realize was exactly how broken the NFS protocol v3 really is. When you open a file, it's not just one round trip to get the file open, it's multiple round trips to get things validated on the open before you can even send the write down. Indeed, a small file workload where you do a POSIX open, read, and then a close takes 4-5 round trips. And that's all going to the same NFS server. And those are all serialized and blocking before a command line program that's doing that read gets to complete. The same is true for a small write workload where you do a create, dump something to a file, and then close it, like echoing something to a file. It takes several serialized round trips to the NFS server before that sequence completes, and that process that does the echo can exit and go on to the next thing within the script, so to speak. Reason I bring this up is because in the technical computing world, media entertainment included, these small file workloads are very common because there's a lot of stuff that's done through POSIX and through scripting kind of stuff, and they're all having to do that. Well, because we're using NFS 4.2, the newer NFS standards, and because the team that I have working on this is the Linux kernel team building this, we've ensured that we're using all of the sophistication in that new protocol to make it possible to get to the theoretical limit of 2 round trips. 1 round trip to the control plane, and then 1 round trip to do the data. And that's true for both the small file read as well as the small file write. And notice, not only is it reducing it from 4, 5, and 6 round trips to just 2, but those 2 are distributed across different systems. One, on the data access, you've got full n-way concurrency on that. And on the control plane, it's going to a separate control plane than the data plane. So the net result of this is that we fully expect to be much, much faster, and this is what we're proving out, much, much faster, even for small file workloads, than traditional scale-out NAS or NAS systems.
Well, would that not be quite tricky when you're creating new files? Because you'd almost have to go and say, does that file exist? Is that directory available? You know, I want to create it, so you lock out the new name and before you write, or you decide you don't take that risk and you do all the creation and then throw it at the file system,
So
assuming
luckily,
you can
those things are contemplated in the protocol where you can do a create in one of 2 modes. One is to where it fails if it already exists, and the other one where it ignores whether it exists or not and creates it over top. And what the protocol allows one to do is called compound operations. So we can create the file and get a layout to be able to go and write it, get the routing information all in one fell swoop, and get the delegation that gives the client the definitive say of the state of that file. So handing out the delegation, handing out the routing information, and getting the file created or open can all be done in a single compound, one round trip.
And there's no risk to losing the content if the server fails halfway through, or
Nope.
there's some sort of...
It's still all atomic on the thing.
Right.
So this, I have to admit, this wasn't until about 6 months ago I realized this as we were getting into it. And I started pounding the team of how we can be better about this. Did we actually realize that we can exceed the capabilities of traditional NFS significantly, even on small file workloads? Now it's relevant in the media and entertainment space, but the chip design world, also a big scale-out NAS user and something I consider part of the broader technical computing, the EDA chip design world is even worse at small file workloads, where this is very relevant. Okay. Any questions? So from a performance perspective, it's a night and day difference to be able to spread the load at the I/O request basis, at the object granular basis, collapse out the many layers, even collapse out the networking completely so that the data is being routed to server local. This makes a very big difference. And let me jump forward to cost just to make a note here, because I might fail to note it later. We went through with all of our customers. We have a very disciplined sales team, thanks to Casey, and he forces the sales team to do things that aren't comfortable to them, which is to sit down with a customer and say, here's what we think we're going to save you, and here's what we want to charge you, and do that early to make sure there's an agreement about what kind of value is being brought to them. We did this with one of the M&E guys, and the numbers were large. We said, look, we're going to save you this huge bundle of money, and the customer said, oh, so you want to charge me something just under that? We're like, no, it'll be more reasonable than that. And they were actually good with it. But the customer came back and said, okay, I get it, and now I'm going to sell this to my CFO, and you forgot, in your analysis, you forgot to include the fact that when you do this, you're not only saving me the cost of these different layers and letting me get my performance in a cheaper fashion from a storage perspective, because now I don't have to expand my Isilon, I don't have to add the cache, I don't have to do all this other stuff. They said, you're forgetting the fact that if you're delivering that kind of performance, my rendering farm is more efficient and I can probably reduce it by at least 20%. So now we're talking about saving money on the compute side because it's not sitting idle as long either. So performance has a direct savings on the rest of the infrastructure because you're not sitting with the CPU idle there. Okay. Cheat again here. I apologize. Okay. From a manageability perspective, We talked about the fact that managing their own namespace virtualization is, by their own admission, a nightmare because it's very difficult to ensure that applications are seeing the facade instead of the actual storage systems. And when you start moving around the actual storage system, if they accidentally bound to the real path instead of the symbolic link, they're screwed. And that invariably happens, and they don't discover it until they try to switch something out from underneath and things were bound to the wrong path. You have the inherent trouble in manageability in that you've got this system with so many layers with different players responsible for how they work. Oh, and another thing, when you introduce these caches, the already lax NFS consistency model gets even worse. They have to put something like 5-minute timeouts from one job to the next to make sure that the cache has flushed before the next job starts that might access those same files. See, in NFS you have a closed to open consistency. If I have two guys accessing the same file, the only way to guarantee that a subsequent access from somewhere else can get the stuff that the first guy wrote is to have him close it. It's called closed to open consistency. So somebody writes a file, when he closes it, it's guaranteed that if somebody else opens it, he will at that point see what the first one wrote. There's no guarantee if he opens it before the other guy closes it. That's fairly lax already. But now can you imagine if on one of my nodes I run a job that builds a file, and then on another node, I go to read that file immediately afterwards. He's done writing it, he's closed it out. I go to read it on the other one, and it ain't there. Because you end up going through a different cache, and the cache hasn't flushed it yet, and it hasn't gotten consistent. In other words, these caches break the consistency model. Even NFS is already loose one.
Wouldn't that be the case with the gateways down below?
The gateways, because they're incorporated as part of this system, they use the sophisticated locking and stuff. That's what leads to the lock contention if you're accessing the same object. So they take care of it at the cost of bouncing locks and other stuff, while the caches don't.
And I guess that the gateways share their cache information, so they know that the data might be on another node, and then they just reroute and just get it from that one.
And they make sure the lock and the flushing, right, exactly.
Yeah. And you're saying the vendors that do the caching can't do that?
They can't. They don't end up doing it because the caches are optional, and somebody might even be going directly to the storage. So it's kind of inherent in the model that they can't be, which means if they're write caching, you have to, what you do is you configure the caches to a certain flush window, and you say you have to guarantee that everything that you're write caching gets flushed within 5 minutes. And then the guys running the cluster have to make sure that any consumer of a file that somebody else supplied waits 5 minutes. And so they actually do their job scheduling with all of this mess.
And is this, are you talking about the caching layer? Are you talking about a cache supplied by Isilon or by some other vendor?
These are typically other vendors.
I'm just trying to understand why they can't have the same locking.
Because they're optional caches. They're optional. And if you're trying to do a read cache that's an option on or not, then you inherently have data skew with the actual storage.
I think the other thing, Curtis, is that
and to make these things scale out,
exist.
Right.
And because he doesn't know they exist, he can't say that he knows that the data that's on the Isilon is the last image, and if not, reboot you up to the cache to read it. He
Right.
just
I think,
know they exist.
but that's only a problem if you've got clients that are going directly to the Isilon.
or you have caches that aren't connected to each other.
Yeah.
Well,
which is generally the case.
Which I'm saying I don't understand why they wouldn't be connected to.
You could potentially make the caches more sophisticated that way. What I'm telling you is that the main vendors of these don't have that sophistication. And that what the media and entertainment and other folks that use these have to do is make sure that a consumer of something that was just written doesn't start for at least 5 minutes. And that happens at each stage of this. Yeah.
Yeah.
Could it be
you know,
fixed?
Unfortunately,
with your-
it's one vendor talking about another vendor, so I have to
Go and
filter
check.
it through that filter.
Yeah, no, but this is coming from the customers of what they have to do when they schedule their jobs, which adds to a manageability issue. Yeah. So we've talked about the difficulty in isolating different pieces of data to know what needs to be archived, what can be discarded, et cetera. Many of these guys have, they take many iterations to refine that. Related to that is the difficulty in finding who's consuming the bulk of the resources. Not only do you have the issue with hotspots and routing, but it's a black box. There's not really a good way to say what application is causing the load that's being constrained. So it ends up being a hunt in the dark to try to figure when you have a resource over allocation issue. Capacity, fairly easy to see which files are big and who's hogging the capacity to know who you need to go look at to victimize, to get rid of their shit so that there's room for somebody else. But if I have a performance issue, you're running completely blind. And that is a very big issue of no visibility. We've had customers say, if all you did was give me the telemetry stuff you had there, it's already worth it. Give me the ability to see which of my clients and accessing which objects are swamping the system, because the type of crap they deal with is that somebody, one of their programmers who's writing this stuff, or somebody using existing programmers, asks it to do something that overloads the system, and they're screwed. There's two things that we do here. One is the fact that when we split the control plane from the data plane, we've instrumented it with telemetry so that we can track what the data plane is seeing from a performance and load perspective. And we chart that historically and record it. So you can look at which files are being accessed by which clients, both now and in the past, and chart those things to look for when there's a significant increase and on which objects and which clients. The second thing is the ability for our system to put constraints on the amount of bandwidth or ops that a given object is entitled to, and therefore set a form of QoS, put a box around him. So that's a very, not only do you not have visibility, but there's no control over who consumes the performance. And here we add both of those with the telemetry tracking and the ability to constrain which objects get what access. Questions about this?
So that was always a problem with traditional sort of monolithic virtualization, like SVC and Hitachi's virtualization, that you could overwhelm that
Indeed.
controller piece without any problem.
That's true. And this carries over to many other markets, because you want to be able to guarantee QoS. You want to be able to constrain things that shouldn't have the ability to pig out and swamp the rest of the system. When you compound that with the hotspot problem and the routing thing, it can get very hard to track these things down to see who's doing that.
Yeah, we used to see problems where you could build a layer, the virtualization layer would have more capability than the storage layer. Mm-hmm. So the cache would build up, and it would get to a point where it couldn't service flushing to disk fast enough, and then you'd have a real problem.
Then everybody gets queued up and they're stuck behind it. So that's also a big management, because as an admin, most of these guys spend their time on two things. I'm running out of space. How do I go and recover space? Somebody's complaining about performance. How do I go and find who's consuming all my performance and how to keep them from killing the system? In other words, as an admin, what you're doing is trying to do the resource allocation, not just of capacity resources, but also performance resources. And the tools that are available today for managing those performance resources are next to non-existent. So finally, let's talk about cost. On the cost side, we've talked about how performance inherently improves the cost on the compute side. We also have the fact that a single tier architecture avoids all of these intermediary boxes and lets you collapse them. But let me draw specific to the point of, let's just talk about counting network ports. When here I've got one network port in my storage infrastructure that I need to supply, forget the caching and all of that, if all I have is the Isilon, that Isilon triples the port count because I have to come into and go out of the gateway before I go into the back end. So you go from 1 port to 3 network ports just to maintain the same bandwidth through. That means the inherent cost structure of this form of scale-out NAS is inherently massively disadvantaged versus being able to route the data at the point of origin and avoid the indirection through a bump in the wire, a box that you have to go through. Not only the network portage, but also the CPU and the other, the memory complex here that has to bounce the data on and off the wire, and et cetera. All of those go away when you're doing it in software with a separate control plane. Additional factors to cost. So collapsing the layers. I should point out that this is your most efficient way, especially coming from Fusion I/O. The best way to get bandwidth is to have it attached to your peripheral bus or even your memory bus and not have to go over the network at all. And this contemplates being able to incorporate that to get very high bandwidth. The fact that this is a software-defined solution, primary data is not selling hardware, so you can use commodity off-the-shelf servers as these storage nodes. We're not dictating specific custom hardware like the caching guys or the scale-out storage guys. Here's another very real impact. Because it's so difficult to manage the migration from one storage system to the other when you go to decommission and commission something else in its place, invariably, customers find themselves being held hostage for 4th-year support. And if you know the storage industry, when something goes out of the standard support period, you end up paying through the nose. And while they would love to decommission and buy new storage, many of them had said, for the cost of my 4th-year support and all, I could buy new storage from some other vendor that had better capabilities. But I'm still going to support and pay the high support fees because I can't decommission this thing because I don't know what all workloads are on it and how to get them off. Have you heard these stories before? Yeah, okay, so I'm preaching to the choir, sorry.
It is changing though. You can see a couple of vendors flatlining the support fees.
Yes, yeah. But let's take it one step further. Let's suppose that with data virtualization and our automated orchestration to do the distribution of data, that the cost of adding in new storage and taking it out from a manageability perspective goes to 0. Now you can talk about refresh cycles that are on the few months time frame. And you can talk about business models where you're leasing the storage. Because there's no friction to the migration path, it's easy just to jump off of whatever and jump on to the next best thing. So this has real implications when you reduce the friction for moving forward to newer generations. You can even change the business model to where now you're leasing storage and you're not buying it. Okay. Well, let me make sure I covered everything I wanted to cover. I'm pretty sure I did, but yep. We talked about, the last thing is the object storage. If it's all part of the same namespace and as simple as changing some of the objectives on the data and having the orchestration, moving it off into the cloud, it makes it much easier to take your dark data out. And with the sophistication in the control plane, with intelligent metadata, you can much easier identify which files can be discarded entirely. So not only can you get cheaper performance by moving things forward to the server, you can get cheaper capacity by knowing what you can discard and knowing what can be destaged into the cloud efficiently. And because data can migrate very fast, you don't have to over-provision the infrastructure because you can quickly mux different data sets to your archival tier and back. All right. So net of it is very significant improvements just by introducing primary data on performance, on the manageability, and on cost. I like to talk about it as reducing stuff, reducing staff, and reducing the stalls in getting your job done, because time, equipment, and manpower are the main costs to running any of this stuff. Very significant improvements, and it was fun telling you about it. Let me wrap up just by asking one more time if there's any questions. Yes.
One last question. All of the stuff you've shown us is very, very NFS specific.
Let me be clear. That's because here we've been talking about the technical computing market.
That's why. That's the exact question. Is that because
we could have a similar discussion if we talk about the VMware market or the business market? In their case, we're talking more about SANs and other things.
Yeah.
So this was intentionally wanting to get down into the detail of a specific customer where they're used to specific protocols. In the Windows world, for example, all of these same benefits are possible by having an agent in Windows that does the data routing. So we don't change the SMB protocol. And if you don't mind going through an intermediary, you don't have to add anything to your Windows box. But if you want to get the very high performance, then you load an agent in Windows that's a standard filter driver, supported and everything, and that gives it the concurrency a similar way. Okay. So whether you're talking about VMware or Windows, there's similar solutions and compelling as here in the Linux-y cluster space. Yes?
And you talked about getting rid of staff and stuff, and I'm going to go slowness.
Stalls.
What?
Stalls.
Oh, stalls, nice. I missed the part where you got rid of stuff. Like I know that you talked about.
You're getting rid of all of these layers. You're getting rid of network ports.
Oh, okay.
You're even getting rid of whole boxes by using server local media.
Okay, you're not.
And you're getting rid of
data.
over provisioning because now I can very quickly move data sets in an automated fashion, so I'm not having to over provision.
But what about you talked about that you've got a bunch of statistics and stuff on usage and all of that. Mm-hmm. What do you do with that data? Can you then migrate that stuff out?
The fun part about it is what we've done is we've taken all of the metadata, data about the data, including the history of past access, right? And have made that available as part of the predicates that you can use when it comes to finding subsets of the data to do certain things with it. So you can use the fact that, hey, this thing hasn't been accessed in a year, so therefore I'm going to set an objective on it that allows it to be destaged into the cloud, right? Or you could even have something that looks at the duty cycle and determines that this thing is used once a month on the first Monday, and set up a schedule that on the day before that, it gets moved, the data set gets moved into where it gets high performance access, and the rest of the time it's off in
And
in
you
slow.
manage that move?
Yes.
Okay.
That goes to the fact that we can move data live without interrupting the access. So the core underpinning to this is the data virtualization, being able to place anything on any storage and move it at any time without interrupting the access to it, and while still preserving the sophisticated data services like snaps and clones and async replication, et cetera. So there's really the two layers, the virtualization, putting anything anywhere, being able to move it at any time, and then the orchestration, which is doing the analysis of what should go where and making sure things are at the right place at the right time.
I would think orchestration and analysis would be different.
Analysis is different. The visualization piece, orchestration is where you take what you would present to an admin so that he could orchestrate it manually, and we use it in the loop so that it automatically does it based on looking at the same sorts of things. Because it's kind of like, I love this analogy, I'll bring it up here at the end. Casey pointed out the other day. You talk to Google, Google isn't building a car, a self-driving car. No, they're building the driver. We're not building the storage at the end of the day. What we're building with the orchestration is building a substitute for the storage admin so that his job gets fully automated, making sure data sets get moved to the right place at the right time for his constituency to go and access it and use it. So the orchestration is taking the telemetry and other feedback and allows you to put it in the loop to where it controls automatically when the data sets get moved to be in place and used.
If you have repeatable analytics, and they probably do in this industry, then that makes sense. But otherwise, analytics on what's in your, what you're storing, I guess probably a lot of the time it would be repeatable. You're looking for the same, you're doing the same things over and over again. So
you're looking for hotspots, you're trying to put limits on what.
Spots. You're looking, and all of that information is stored where? Your software, where are you storing that?
In DataSphere. DataSphere is using a very sophisticated time series database for recording the access history.
What's the database technology in DataSphere?
Underneath the covers, we're using InfluxDB, actually.
Okay.
InfluxDB is one of the tools that we're using for storing the actual historic samples. Great question, yeah. InfluxDB is nice because it lets you slice and dice the time history based on many different keys.
Right.
So I could look at clients.
Are you assigning tags then, or doing?
That's the exact term they use there, tags.
Okay.
And that lets you dice it by which client, which object, which storage container.
So do you have to walk file systems then to assign tags?
No, this is
that should be where the tags are. So, but the tags have to be updated over time because they're.
As the samples come in, they get put into the time series database under the tags of the inode, the client, the storage container, et cetera. Yeah.